Okay, so for gas and gas stoichiometry, question type 7 is going to be a lot more work than what we're used to doing. And that's because this is going to be part combustion analysis and part gas law. Okay, so we haven't really solved any combustion analysis questions up until now. So if we look here, we're given 42.85% carbon, 7.20% hydrogen, and 49.95% nitrogen. This information here is going to allow us to figure out the empirical formula of our compound. So to do that, what we have to do is we have to assume that we had 100 grams of this compound that we analyzed. So that allows us to convert our percentages directly into grams. 42.85 grams carbon, 7.20 grams hydrogen, and 49.95 grams nitrogen. Then we convert these to moles. Divide by the molar mass of each compound or element. And if we do that, we're going to take the 42.85 grams of carbon divided by 12.01 grams of carbon and end up getting 3.567 moles of carbon. For hydrogen, we take the 7.20 divided by 1.008 grams hydrogen per 1 mole hydrogen. That's going to give us a 7.143 moles of hydrogen. Take the nitrogen, divide that by 14.01 grams nitrogen per 1 mole nitrogen. That's then going to give us 3.565 moles of nitrogen. Now, to get a ratio here, we divide by the smallest number of moles, which is going to be 3.565. That makes us approximately 1 mole ratio for carbon. For hydrogen, that will be 2, and then for nitrogen, that will be 1. So my empirical formula is C1H2N1. So we'll put that in. Okay, so remember typing it into a calculator, you would be CH2N. That's how we want to write that format for the empirical formula. And what we need to do, though, is find the molecular formula. It's still the question of the day. Well, before we do that, I want to find the empirical formula mass. Because if I know what the empirical formula mass is, I can then use that as a conversion factor to find the ratio of the molecular formula mass to the empirical formula mass, so I can find out what my molecular formula is from my empirical formula. Well, if we look this up real quick and do the quick calculations, it's going to turn out to be 28.04 grams per mole. So now we have to solve for the molecular formula. In order to do that, we need to use the rest of this information up here to solve the ideal gas law. Okay, so PV equals nRT. We're given mass of the sample, volume in milliliters, pressure in atmospheres, temperature in degrees Celsius. Okay, if we take the mass divided by the number of moles, that gives us the molar mass of the molecular compound. So we need to solve the ideal gas law for N. So PV over RT. Well, let's do some quick math, right? 760 millimeters of mercury is the same as 1 atmosphere. 1.00 atmospheres. The volume is 250 milliliters, which is the same thing as writing 0.250 liters. R is 0.08206 LATM mole Kelvin, and the temperature is 273 plus 100, so that's 373 Kelvin. This now tells me that my N, the number of moles present, is going to be 0.008167 moles. If I take the mass divided by moles, that's going to be 0.915 grams divided by 0.008167 moles, and it's going to be 112 grams per mole. So my ratio of molecular formula mass divided by the empirical formula mass is going to be 112 grams per mole divided by 28.04 grams per mole, which is about 4 times larger. Therefore, I'll have 4 times the formula for C1H2N1 for my compound. So that would be C4H8N4. To type that answer in, C4H8N4. That's the answer I would type in to the computer. Alright, now if you thought there was just going to be a lot of questions, you're right. You get to do the next question 3 times minimum. Okay, question type 8. We take an unbalanced equation. Then we're going to ask for what volume of one of the reagents we would require to react with a certain mass or volume of another reagent at certain conditions. Okay, so first things first, we got to balance our equation. Turns out to be, if we balance this, there's 1 mole of C4H8 for every 6 moles of O2 produces 4 moles of CO2 and 4 moles of H2O. Now, let's find out how many moles of oxygen we're going to make or need for this. So 0.952 grams C4H8. Divide that by the molar mass of C4H8, which is 56.104 grams per 1 mole C4H8. Our molar conversion here is 1 mole of C4H8 to 6 moles O2. And we plug this into our calculator and we find out that we need 0.1018 moles of O2. Now, I'm not going to round here. Okay, I'm going to take one more significant figure than what I need for my calculations so we don't have any rounding errors early. The question asks for the volume of O2. Well, that means I need to solve the ideal gas law for volume equals nRT over P. Right? Need to do some conversions, right? Well, we have the number of moles, 0.1018 moles of O2. We know the R value by heart. It's going to be 0.08206 liter atmospheres per mole Kelvin. Because we're doing the temperature, we need to add 71 plus 273 Kelvin. And then we're going to take 318 millimeters of mercury and divide that by 760 millimeters of mercury per atmosphere. Okay, plug this into your calculator, you get 6.87 liters volume for this reaction at those conditions.